Nat 4-5 Physics, Velocity Time Graphs. The key areas we will cover today are velocity time graphs, graph shapes, acceleration, deceleration, and constant speed, and calculating the area under a graph. Velocity time graphs. A velocity time graph, or speed time graph, is a useful way to describe the motion of an object. The shape of the graph can show you if the object is speeding up, which is acceleration, is slowing down, which is deceleration, or if it has a constant velocity or speed. Here is a graph showing speeding up, so acceleration. We can see here that we're starting at a low velocity and the velocity is increasing over time. This is a positive gradient and shows the object speeding up. Now we have a graph showing an object slowing down. We can see this is the opposite of our previous graph. Initially, the object starts at a high speed, the speed then reduces over time, so our object is slowing down or decelerating, and this is a negative gradient. Finally, we have a constant velocity. If our object is going at a constant velocity, you can see this is a straight line. This is zero change in velocity over time, so the gradient is zero. So these are the only three shapes that you need to remember. An upward slope, meaning acceleration, a downward slope, meaning deceleration, and a horizontal line, meaning a constant velocity or speed. Now let's have a look at the calculations we can do. Velocity or speed time graphs are also useful as they allow you to calculate the displacement or distance for a journey. To do this, you need to find the area under a graph. We have three graphs just here we could have a quick look at. The first graph shows us the area as a rectangle or square. Here, the distance is equal to the area under the graph, which we always need to write with calculations like these, and because it's the area of a rectangle, we know it's the base times the height that gets us to the area. So writing this down, we know that our base is equal to 15. We can see 15 just here. Our height is equal to 4. We can see that on the graph just here. And so popping it into our equation, distance equals the base times the height, which is 15 multiplied by 4, which is 60, and because it's distance, that's in meters. The next graph, and the final one, showed us the area as a right-angled triangle. Just here, we know that distance is the area under the graph, as always, and the area of a triangle is a half times the base times the height. So here, we can see the base is 15 again, and the height this time is between 0 and 6, so this is the full height of the triangle. Our distance, because it's equal to the area under the graph, is equal to a half times 15 times by 6. Popping that into my calculator, a half times 15 times 6 is equal to 45. And again, because that's a distance, that's in meters. Example 1. The speed time graph for an object is shown below. Calculate the distance travelled by the object in 3 seconds. You can see here that unlike before, our graph is actually made up of more than one shape, and we've got a dotted line between the two shapes to show this more obviously. So what we can do is label each of these shapes. We've got shape 1 and shape 2. Shape 1 is a rectangle and shape 2 is a triangle, and to calculate the distance travelled, that's what they want us to calculate just here, by the object, we want to work out the area under the graph for each shape. So first of all, we want to write distance equals the area under the graph. So if you're doing a question in a homework or a test like this, whoever's marking it understands that you know why you're calculating the area, because it's the distance. So now we can split this down. We can look at area 1, which is a rectangle, so we are doing the base times the height, which is equal to, we've got 0.5 here at the base, and the height is 0 up to 30 just there. 0.5 times 30 is equal to 15, and because it's a distance that we're calculating, that's going to be in meters, because you can see our speed is in meters per second and our time is in seconds. Let's look at shape 2. We want to do a half times the base times the height because it's a triangle. So we've got a half. Our base It's not the full 3 seconds, even though that's our end point just here. We want to go from 0.5 to 3, and that's our base of our triangle. So between 0.5 and 3 is 2.5, and the height, the full height of the triangle is again 30. So a half times 2.5 times by 30 is equal to 37.5. And again, that's meters. And to get the total distance travelled, what we want to do is add 15 and 37.5 together. That comes to an answer of 52.5 meters. Example 2. The velocity time graph for an object is shown below. Calculate the displacement after 4 seconds. We can see that our line starts up at the 6 here, ends at the 2. What people often think is we just need to calculate the area of this triangle here. But what we need to do is actually calculate the whole area under the graph, so all the way down to the 0 point. What we can do here is add some dotted lines, so one running across just here to create a triangle, and one running down from this point here to create a rectangle. Let's label these shapes 1 and 2. As always, we need to write distance equals area under graph, or in this case, displacement, as it's a velocity time graph, so that's equal to our area under the graph. Let's go for area 1 to begin with. It's a triangle, so we are doing a half times the base times the height, which is a half times by our base is all the way from 0 to 4, and our height is just between the 2 and the 6 just there. So that's just the height of our triangle. We're not including the rectangle underneath. The difference between 6 and 2 is 4, so that's what we're putting in here. A half times 4 is equal to 8, so that'll be 8 meters. For shape 2, it's a rectangle, so we want to just do base times height. Our base is 4, the same as before, and this time it's between 0 and 2. So 4 times 2, again, is equal to 8 meters. To get our total displacement, what we want to do is add the 8 and the 8 together, and that gives us 16 meters. Example 3. The velocity time graph for a dropped ball, which bounces several times, is shown below. Explain the motion of the ball between A, O and P, B, Q and R, and C, R and S. First of all, it'll be useful for us to draw a quick diagram of what's actually happening. First of all, the ball is falling, it's dropped, so they're not throwing it up in the air, they are just holding it out and let it go. Eventually, the ball is going to hit the ground. After this, the ball will bounce off the ground and move upwards, and eventually it's going to reach its highest point, which won't quite be the same height as before, but it will still be the highest point it can reach. After this, the ball is going to then travel downwards again, and this is going to carry on happening. You can see this is going to repeat. Everyone's dropped a ball before. You let go and it bounces. So we need to explain the motion of the ball between O and P to begin with. Between O and P, we can see there is an increase in velocity on the graph, and that's because when you let go of the ball, it gets faster as it moves towards the ground. So what we can say is the ball is accelerating towards the ground. Let's look at the next parts between Q and R. After the ball has accelerated towards the ground, eventually it's going to hit the ground, and it's going to have quite a high speed when it does that. We can see on the graph that P and Q look to be at approximately the same distance from that 0 line in the middle, but on opposite sides. So initially we've got a high speed moving down the way, and then we have a high speed moving up the way. So it's the same number for the velocity, but in opposite directions. So we know at Q, the ball is just leaving the ground at that point. It's this point just here. it's starting to bounce back up again. As it travels up the way, we can see the velocity decreases towards 0. That's what this line is showing here. And at point R, the velocity is 0. We know that as the ball travels upwards, this velocity is going to decrease until it reaches 0 at its highest point. So the way we're going to write this is, at Q, the ball leaves the ground. And at R, the ball is at its highest point. Now let's think about what's happening between R and S. If the ball has just reached its highest point again, at R, we know that after that it's going to start falling again, and this mimics what was happening between O and P. So between R and S, if the ball is falling, again it's accelerating towards the ground. So that's how we're going to write this between R and S. The ball is accelerating towards the ground. You can see on the graph that this pattern repeats again and again and again, but the total height just here of P, of S, and then the subsequent peaks is reducing. And this is because the ball's losing energy. So you let go of the ball, it bounces, it bounces, it bounces, but it doesn't keep bouncing to the same height. That reduces again and again and again until your ball eventually is just sitting on the floor. That's why these peaks are reducing there. Let's look at some review questions. Question 1. A balloon's speed time graph is shown below. Calculate the height of the balloon after 100 seconds. This question is asking us to calculate the height of a balloon, which we can also label as the distance that the balloon has travelled if we presume the balloon is travelling straight up in the air. So presuming that the height is equal to the distance, we can also say that distance equals area under a graph. And we have a graph just here, the speed time graph. So distance equals area under a speed time graph specifically. And we can see that this graph is split up into two shapes. Let's label these shapes shape A and shape B. And now let's calculate the area in each shape. So for shape A, we can see it's a triangle, so our area is a half times the base times the height. So that's equal to a half times, we've conveniently got some labels along the bottom of this axis. So we've got between 0 and 60 as our base, and between 0 and 6 is our height. So a half times 60 times 6 is equal to 180. So that's the area of shape A. And because this is equal to a distance, we can put m after this for meters. Let's look at shape B. It's a rectangle, so we know we're multiplying base by height. Our base is not 100, it's between 60 and 100, this distance just here. Between 60 and 100 is 40, and our height is 6 again. So 40 by 6 is 240 meters. To get our total distance, we need to have our total area. So all we need to do is add up our two numbers. 180 plus 240. That is equal to 420 meters altogether. Question 2. The velocity time graph for a boat's motion during a rowing event is shown below. Calculate the boat's displacement during the event. We know that calculating displacement is, again, the area under the graph, so that's what we can write first. And looking at our graph, we can see this time it's split into three different shapes. So again, let's label our shapes shape A, shape B, and shape C. First of all, shape A. Our area is equal to a half base times the height because it's a triangle. And we can see that our base is 25 and our height is 4.8. So a half times 25 times 4.8 is equal to 60 this time. Shape B is a rectangle, so it's just going to be base times height. The base is between 25 and 450, so that's 425. And our height is still 4.8. 425 times 4.8 is equal to 2040. And again, that's in meters. And shape C is another triangle, so a half times the base times the height is what we want to use to calculate the area of this. So we're doing a half times our base is between 450 and 510, so that's 60 just there, and our height again is still 4.8. So a half times by 60 times by 4.8, I'm just going to pop that into a calculator. A half by 60 times 4.8 is equal to 144, again in meters. If we want to calculate the boat's total displacement, we want to add these three numbers up together. So 60 plus 2040 plus 144 altogether is 2244. And that's in meters again, so that's our final answer. Question 3. Explain which of the following graphs represents a ball being thrown into the air and returning to the thrower's hand. We've got two different graphs here, one that looks like a straight line and one that looks like a bit of a zigzag. Let's have a think about what the ball is doing when we throw it into the air. So drawing ourselves a little diagram, we've got a ball and initially it's thrown upwards. Eventually it's going to reach a peak, and then after that it's going to fall downwards again. Once the ball is thrown upwards, we can think at the initial point it's got quite a high velocity. Imagine you swing your hand down, swing it up, and then just before you let go of the ball, your hand is going at quite a rate, and when you let go of the ball's going quite fast. So that's one of the points we can note down. So if the ball starts with a high velocity and travels upwards to a point where it stops, it must be slowing down. So the ball is slowing down or decelerating. Once the ball reaches its highest point, it's going to then start falling again. And when it starts falling, it's going to have an increase in speed, so the opposite of what it's already just done. So the ball will accelerate. So looking at these three sentences, initially the ball starts with a high velocity. The ball then decelerates or slows down as it travels upwards, and then after the ball gets to its highest point, where it's at a speed of 0, it's going to fall, which means it's accelerating downwards. Looking at our graph, we have for graph A starting point just here, and for graph B a starting point just here. So we can see on graph B, the ball starts with a velocity of 0, whereas on graph A, we have a high velocity, but it's negative. But that's okay, our velocity can be negative, we just need it to have a high kind of magnitude for that number. The negative or positive just shows what direction it's going in, so whether that's up or down. So our initial point shows that graph A is right, but let's check with points 2 and 3. The ball is decelerating or slowing down. We can see that just here, we start at a high velocity and then move towards 0. So the ball is starting with a high velocity, a high number, and that number is decreasing towards 0. So yes, that's showing deceleration. For graph B, we can see this line moving upwards here. It's going from 0 to a high velocity. That's actually an increase, that's an acceleration. So again, we know that's wrong for the second graph. Third point, the ball gets to its highest point at a velocity of 0. We can see that's the case here, but not the case here. And after it gets to its highest point, it's going to fall, accelerating down the way. Looking at this graph, it looks like the ball is starting at 0 meters per second, if that's what it's being measured in, and then the velocity is increasing, so we've got an acceleration just there. So overall, we know that graph A represents a ball being thrown into the air and returning to the thrower's hand. You may recognize graph B from earlier in this presentation, and this is actually a graph for holding a ball out and dropping it, so the ball's initial movement is down the way, whereas in this question, the ball's initial movement was up the way.